right? BA
Yes.
cosine theta.
Yes.
So now I think the thing to do would be to maybe split this into two parts, right? So we got this part here with the gray shading, and maybe this part up here with this green shading. You know what I'm saying?
Yeah.
So we've got this area and that area. All right. So now in this case, it looks like the magnetic field makes a 45 degree. So for the lower portion, if I could draw just the lower portion, right? The area vector is this way, and the B field is this way by 45 degrees, right?
Yes.
Yeah.
So for this one, I see that the area vector is this way, the B field is this way, and the angle is 45 degrees. That's going to be useful because it tells me this.
Okay.
All right. Now over here, for the other one, let's see what we got. The area vector is down. I should be careful, that's an area vector. This is the B field vector. And then here, it's still 45 degrees. Right?
And do we need to pay attention to like negative 45 degrees and stuff like that?
Maybe. So, because if they're exactly opposite, do you agree there's no? So let me put it this way: if this induced EMF has the opposite polarity of this EMF, then there's no induced current. Agreed?
So now, are the currents just competing with each other to equal like a net of zero?
Well, so that's what we're asking. We're asking, do they, right? Are you going to try and induce currents in opposite directions and thus have no, or are you going to induce them in the same and have double?
Okay.
Agreed? So that's kind of our question here. So let's think about this. According to this loop, you're reducing the number of these, whatever those are. You're right. Let me rephrase. The B field is originally to the right, and you're going to reduce that. Agreed? So that means you're going to try and flow current this way to keep the rightness going, so to speak. Am I losing you?
Yeah.
Okay. All right. So think about this. From this loop's perspective, essentially you've got a bunch of these little B fields coming through it, and we don't need to worry about the part that's in plane. I don't need to worry about this component. I only need to worry about this component, right? Maybe I'll draw these as dotted lines, right?
I don't think I understand the components yet.
Okay,
Like the
well,
area
do you agree
vector.
that the B field is pointing both this way and that way? Right? It's down and to the right?
Just like vector-wise?
Yeah, just vector-wise.
Yeah.
Okay, so if it's pointing down and to the right, this part doesn't matter because it's perpendicular to A, and this part does matter, right? This is basically B cosine 45, if you will. It's this portion right there. B and the cosine. So this is the part that's pointing through the loop. It's the B that's parallel to the area vector. Okay, so now over time what's going to happen is that's going to go away. Isn't that what you said? So over time it's going to go away, and let's say there's only one of these after a little bit, right? I reduced the number of right arrows in the magnetic flux. Therefore, I want to create right arrows, so this current should tend to flow this way. So that means the induced current should flow this way to try and create.
It's opposing the change.
It's opposing the change. I lost B field to the right. That's why I was trying to say I lost rightness. So I'm trying to put back rightness.
Okay.
That was my way of trying to say that. I didn't know there was a lot of dense words, but maybe just saying all that is better. Is that cool? Where this is I induced and these are B induced. Is that cool? So according to this, we expect it's going to flow. I'm going to say this is a dot and this is a triangle just so I can talk about it. This one indicates current would flow from the dot to the triangle. So if I drew a little dot here and a little triangle here, that's what we would expect. Let's see, this is still the dot and this is the triangle. If this one tries to make current flow from the dot to the triangle, they would cancel out, right? Because they're pushing current the opposite way. This one would be trying to make it flow this way. This one would be trying to make it flow that way. They would cancel out. However, if this one tends to make current flow from the triangle to the dot, we know they would add together. Okay with that?
Okay.
All right. So now let's do the same type of thing. I need to get the components of B, right? And so initially, let me just draw two of these again. Circle, triangle, circle, triangle. So initially, I need to worry about which component, the horizontal or the vertical? Vertical. So we originally got this. And afterwards, it's only going to be, say, one of them. So then the induced magnetic field points which way?
Down.
Down. Tries to keep things the way it used to be.
It's the B field.
So then that's going to have to flow from the triangle to the circle. Agreed? Which, notice if we look at both pieces, the current would tend to flow this way. So they're adding together. Agreed? Too bad. Zero would have been easier. But, so now we have to do it. All right, so in this special case, do you agree that because in both cases the angle is 45, I don't have to think that much, the induced field would just be double either one of these? So I can either figure out the induced EMF here and then double it, or the induced EMF here and double it. Good?
Okay.
Because they both have this B cosine 45 in it. All right, so now I'm going to do some thinking. Okay, E, let's just do it, is the area is 1/2 of pi r squared. And let's just say this is for this part, okay? Circle.
We didn't think about that on one. No.
That's the area, 1/2 pi r squared, and then I'm going to get a minus dB dt times cosine of 45 degrees. Do you agree with all those terms?
Why did we do the minus?
That's just the definition. Oh, here's the area. That's a
Yeah.
constant, and I know the cosine 45 is there, and so I just lumped all the rest of this together.
Gotcha. Okay.
Yeah. B is the only thing that's changing, so then I know I'll have dB dt. And I just stuck the minus sign there just because I wasn't really thinking.
And we're talking about the change in B of the induced current?
Change
Or the
in B,
induced magnetic
this is the
field?
change of B external. So
That's
in this equation, this has to be B external,
Okay.
right? So the EMF in my loop
Mhm.
relates to the external magnetic field.
Right.
Because the external magnetic field creates a flux through my loop. All right, so that's what we're talking about.
I'm just
Good.
not seeing how B external is changing. Is that not
The
consistent?
problem says it turns
Oh.
off.
Gotcha.
If you read the problem, they say it starts out at this and then it cuts off in this amount of time.
Okay.
So in this case, because it changes uniformly, they're saying you have this B field, right? And it just changes uniformly. Agreed? So in this case, notice that dBdt, if it changes uniformly, equals delta B over delta T, if linear.
We know what final B is 0,
Right.
and that gives us the initial B. Yep.
And notice you
But
get a
then it's already
minus
a
sign,
negative.
which is going to give you a positive here if you care about that, but whatever. So this is the EMF just for half of it. Let's say 1/2, right? And then the EMF for the other half equals the same. EMF total equals pi r squared minus delta B over delta T times cosine 45. Got it? As opposed to these slanted ones when you can't see anything. And then if you look from a rotated side view or a front view, a pure front view, it looks like this. From the pure front, you see just a circle right here, and then this one, you can't see the other circle. It's like this, right? And so now you've got these B fields that are kind of coming down at an angle, which I can't draw.
Mm-hmm.
Good?